Hydrotreating technology was first implemented by refineries in the 1950s. Standard support balls and a few other ceramic support media were used as top-bed grading or hold-down media for over 30 years. However, they suffered from many design flaws, primarily a lack of internal void space, which commonly caused short runs and pressure drops. In 1988, Haldor Topsoe introduced multi-hole ceramics as well as multi-sized rings to address pressure drop issues. However, these filters rely solely on contact filtration to retain the particles, and their cylindrical void space design is very ineffective at filtering out smaller particles. In 1999, Christophase introduced the world's first true filter grading catalysts, the cat trap. This reticulated ceramic filter has a very high void space, and its tortuous pathways with varying pore sizes proved effective at retaining a large range of particle sizes. However, there are three main design flaws with reticulated ceramic catalysts. The first flaw is that larger particles have a tendency to get lodged in the entryways or at any narrow point along the tortuous pathways, rendering large portions of the catalyst useless. The second flaw is that reticulated ceramics can never produce uniform distribution. As you can see, the filter inherently produces a turbulent flow that primarily bypasses the filter. Therefore, particle contact with the filter is minimized. The third flaw can be found in its structural integrity. The strength of the reticulated ceramic comes from the numerous tendon-like walls that disperse the pressure, which means that in larger catalysts, when the void space increases, the structural integrity decreases. Our drop tests concluded that over 2% of the 30 ppi cat trap is turned to dust when dropped from roughly 2 meters. This dusting effect acts as a foulant for the remainder of the bed. In 2001, UNICAT Catalyst Technologies introduced the AFS, the Active Filtration System, series of catalysts. AFS catalysts utilize a honeycomb-like structure which provides a large amount of both surface area and void space. This design also provides very high structural integrity. The very same drop test concluded that only 0.04% of the AFS is turned to dust when dropped from the same height. In addition, this design was chosen because the triangular void chambers pass directly through the interior of the filter, making it very effective in all three filtration methods. In granular filtration, the particles accumulate along the surface of the interior and exterior walls of the filter. In turbulent flow filtration, the particles are wedged in the corners of the filter and gradually fill the entire chamber. In laminar flow filtration, the particles again accumulate along the surface of the walls of the filter. But because the interior chambers pass directly through the catalyst, the direction of the flow is minimally affected until that chamber is full. As you can see, the majority of the flow passes through the triangular void chambers with minimal bypass. AFS therefore acts as a very effective distribution catalyst. Let's look at an actual spent AFS catalyst. You can clearly see that the particles accumulated in the corners and along the interior walls of the chambers, filling 100% of the internal void of the AFS catalyst. The particles accumulated on the exterior surface as well, so that every part of this catalyst was effective. Since 2001, UNICAT has continued developing AFS technology. The standard AFS series comes in a variety of disc sizes ranging from 3 to 150 millimeters. They are offered in a variety of mesh patterns that filter particles ranging from 5 to 2500 microns. Many other series have been developed to be used in hydro-treating applications, in sulfuric acid applications, and in silica trap applications, amongst others. The optimal method of loading AFS is the deep bed filtration method. This method is preferred for two main reasons. It progressively removes particles from large to small, and it significantly increases the amount of surface contact between particle and filter. The deep bed filtration method utilizes a top layer of large mesh filters designed to remove 800 to 2500 micron particles. The following layers would utilize medium mesh filters designed to remove 100 to 800 micron particles. The final layers would utilize small mesh filters designed to remove 5 to 100 micron particles. The primary advantage of using AFS catalysts with the deep bed filtration method comes from the ability to layer smaller diameter filters progressively deeper into the bed. This creates exponentially higher surface contact between particles and filter. Let's look at an actual case where AFS catalysts were loaded using the deep bed filtration method to replace a cat trap loading in a naphtha hydrotreater. This unit's lifetime increased by 200% without increasing the depth of the grading layer. In summary, AFS is the most advanced and comprehensive bed grading technology because it has the most extensive range of filter disc sizes. It has unparalleled crush strength, resulting in minimal dusting and pressure loss. It has uniform triangular void chambers, providing uniform distribution and effective filtration. It has diverse chemistry and carrier base, activating surface area and enabling multifunctionality. It has the longest life cycles, especially in DP-limited reactors. This is why companies such as ExxonMobil, Axens, Total, Phillips 66 and BP have chosen to use AFS, and why you should choose us too.